Hello, everybody. This is the first chapter of first part of chapter 1.5, and we will talk today about homogeneous linear system. So let's just remember from the previous section that our system of linear equations can be written in the matrix form when A is a matrix, multiplies by the vector X, and give the vector B. So, and last time we were talking a lot about the vector B, and we discovered that not all the values of vector B necessarily guarantee this solution. So what if we look at simplest possible vector B? So it's a trivial vector consisting from 0. Would we guarantee to have a solution in this case? So this kind of system, then matrix A multiplied by vector B and give a trivial vector 0, we'll call a homogeneous system. So it's basically represent the system of equations which all have a right-hand side equals 0. And this homogeneous system is very, very convenient to work because we can pretty easily figure out if solution of the system exists. And it exists if and only if the equation have at least one free variable. However, it's not guaranteed the solution. So let's just try to work through our system and try to figure out how to identify this solution. And again, the strategy here is quite straightforward. We take a homogeneous system, write it down as augmented matrix, and reduce it to the echelon form and see if there is at least one pivoting column is missing. If it's missing, we will celebrate and jump in joy because solution exists. If not, we might have a solution, might not, but we have to solve everything. Okay, so let's look at the example, and this is example 1 from the textbook, which you might find challenging, so I will lead you through this example. Again, this is the system of linear equations, and right-hand side of every single equation is equal 0. So we start writing down it as a homogeneous matrix system. AX is equal 0. So this is the augmented matrix of the system, which formed the first row formed by coefficient of x1, the second row formed by coefficient of x2, the third row is formed by coefficient of x3, and the fourth row, column is just the right-hand side of equation. Okay, so let's just start to reduce it to the echelon form. Again, we're starting from the first column, and we start working on this -3 because we want to convert this into 0. But we are lucky because our first row have a 3 as an entrance, so we just add the first row to the second, and it should give us a 0. We can use the similar strategy to eliminate our 6 here and convert it into 0. Again, we take the first row, multiply it by 2, and subtract from the third one. And that should take care of zeros in the first column. Okay, the next order of business, if we want to reduce to echelon form, is this number 9 here. Again, if we want the second column to be a pivoting column, we need it to be a 0. So we can take our second column, multiplied by 3, and add it to the third one, which gives us a desirable 0 in this position. Okay, so we almost were there. We're almost at the echelon form. We just need to have 1s instead of 3s in the first and the second row. So we'll just divide them both by 3, which give us a nice matrix in echelon form. And going back to our theorem over there, we seem to be pretty lucky here. Our third column doesn't have a pivot element, so we seems to be have a free variable here. Our third variable, x3, is a free variable, so the solution exists. It's guaranteed by theorem out there. Okay, but what is this solution? Okay, let's just first confirm the solution exists. So we still have this bottom row, and it's left, can be interpreted as 0 times x1, 0 times x2, 0 times x3, which give us a 0, which happens to be right-hand side. So nice. You can take a breath of air. Solution does exist. So we can go ahead and write down it in terms of our variable x3. Okay, x2 have a right-hand side equals 0, so x2 is equal 0, and x1 can be we can use our first row here to write down equation connecting our variable x1 and x3. And because x3 is our free variable, it will be convenient to write down our x1 in terms of free variable x3. Okay, that's lovely. So we seems to find our solution. I mean, we find infinite number of solution because x3 can be absolutely anything. So let's try to write it down neatly as a vector. So our vector x will have a 3 entry, first variable x1, second variable x2, and third one variable as x3. So let's write them down. So x1 goes over here, x2 is 0, and x3, it's free. So we just write down x3 here. So now let's try to simplify a little and try to factor x3 out. So we basically now writing it down as a linear combination with the weight of x3, or x3 times the vector, we would call it a vector v. So basically what we did here is write down a solution as a product of number and the vector. And again, x3 can be anything, but sometimes it's mentally really hard to think about it. So let's go even further. And because x3 can be absolutely any number, we just replacement that by the letter t. And t can be absolutely number in R. So again, it's just annotations. It just makes you easier for you to think, because when you start to think about x3, your mind will jump into the systems of equation, and it's not always healthy. So here, our solution x is a linear combination of number, any number t, times our vector v, which given by 4/3, 0, and 1. And this kind of equation, because we choose the new parameter t, we call it a parametric vector equation because it's multiplication of parameter t by vector v. And geometrically, actually, our parametric form can be really nicely represented as basically a line which comes through the vector v, because we know that the linear combination, we talk about it earlier in the chapter 1.3, so that the linear combination of single vector, it's just a very long line. Or in other words, we can also say the equation, solution of our equation is the span of vector v, because we know that the span denotes the all possible linear combination of our vector. So one way or another, we find the solution, and you can write it down on these 3 different forms. Which one is up to you, but solutions exist. And next time we talk about part 2, we will talk about non-homogeneous system.